So we saw that the power series expansion, a power series expansion of any function is just its Taylor series. So by this we have the power series expansions that we found for 1 over 1 minus x, 1 over 1 plus x, ln 1 plus x, e to the x, etc. These power series are just the Taylor series of these functions. Still, we suppose we pretend that we didn't already find the power series expansion of e to the x, or the Taylor series of e to the x. And suppose I ask you find the Taylor series expansion for the function f of x e to the x about x equals 0, and prove that it converges to e to the x for every x. We want to find this power series by our new methods, or by understanding by the definition of the Taylor series, and prove that it converges to e to the x using the remainder of Lagrange remainder. Another name for in general for a Taylor series about x equals 0, just it has to be about x equals 0, is the Maclaurin series. So when I could have asked find the Maclaurin series for the function f of x equals e to the x, and when you say Maclaurin, it's automatically about x equals 0. So instead of saying find the Taylor series for the function f of x equals to e to the x about x equals 0. Okay, so we start. So the solution. We start our solution here. So we know that in general the formula for the Taylor series of a function f of x is given as is f of 0 plus f prime at 0 times x plus f double prime of 0 divided by 2 factorial times x squared, and so on. So this is sigma n equals 0 in sigma notation, sigma n equals 0 to infinity, the nth derivative of f at 0 divided by n factorial multiplied by x to the n. So we have, so we start by, actually e to the x is maybe the nicest function to calculate its Taylor series, because we all know the derivative of e to the x is itself. So if you differentiate e to the x again and again and again, it always stays e to the x. The nth derivative of e to the x is e to the x. So the nth derivative for any n of e to the x evaluated at 0 is just 1. Is e to the 0, which is 1. So now substituting these values in the formula for the Taylor series, general formula for a Taylor series of f of x, we get the Taylor series of e to the x as 1 plus x squared over 2 factorials plus ... The general term is going to be xn over n factorial, because the nth derivative at 0 is just 1. Of course, this is the same power series that we obtained before, but now we obtained it using the successive derivatives of f of x. But again, we are not assuming that we found this power series and that we proved that this power series equals to e to the x. So we would like to say now, the second part, we found the Taylor series of e to the x, but we would like to say that this Taylor series of e to the x actually converges to e to the x. Again, without assuming our prior knowledge that by our previous methods that e to the x is equal to its power series expansion, or its Taylor series expansion. So because we know in general, a function might not equal to its Taylor series expansion. So the way to go about this is to use Lagrange remainder. So we have the formula for Lagrange remainder is that says that Rn of x is the nth plus 1 derivative at c divided by n plus 1 factorial times x to the n plus 1, where c is some point between 0 and x. So if we apply this formula to our function f of x, the nth derivative of the nth plus 1 derivative of e to the x is e to the x, so this will be e to the c divided by n plus 1 factorial times the absolute value of x to the n plus 1. We would like to show that this Rn of x go to 0 as n goes to infinity, because this what will give us that e to the x equals to its power series expansion. This is the remainder, or the error of, by definition, this is the error of approximating e to the x by the nth degree, its nth degree Taylor polynomial about x equals 0. But we have a problem, a small problem, first to show that this limit goes to 0 as n goes to infinity. This e to the c, we don't know where it is exactly. So we know just it's between 0 and x. X for the moment is fixed. But actually this c can change with n. For every new n, c changes position. It stays between 0 and x, but it changes, it takes a different value. You get a different c for a new n, for every new n. So now we have x could be positive or negative. So if x is positive, this is the interval between from 0 to x, and c is in between. Or if x is negative, this is the interval between 0 and x is negative, so c will be negative between 0 and x. But we're lucky because e to the x is a very nice function. It's an increasing function. So its maximum value over any interval is the value of e at the right endpoint of that interval. So whether ex is positive or x is negative, again x is fixed, e to the c cannot exceed the value of e to the x at the right endpoint. That right endpoint could be 0 if x is negative, so the maximum value would be 1, or it could be e to the x itself. So let's, if we denote the value of e to the x at the right point of the interval, then by capital M, then we can say that absolute Rn of x is less than or equal m, capital M, multiplied by absolute x to the n plus 1 divided by n plus 1 factorial. So now we have this m is fixed, does not change with n. So now we can, and we know that we use the fact that the limit as n goes to infinity of absolute x to the n plus 1 over n plus 1 factorial is 0. This limit, we proved it when we studied sequences. Actually, you can find it in the video, explained in the video sequences 6. And we said this limit, we showed that this limit is equal to 0. And now, so the limit of m, if you multiply this here by m, is the limit will still be 0. And from this inequality, we get that Rn of x will also go to 0 as n goes to infinity. So this shows that our expansion here is valid. The Taylor series of e to the x indeed converges to e to the x.